Hello, everyone. I am Dr. Avans Lee. Very nice to be connected with you. And it is my honor to help people understand plasma further, as I have designed and ran the plasma smelting plant to extract PGM, the platinum group metals in South Korea. Today's theme here is how to generate the plasma engineering points of view. I will focus on the principles. Main contents of my clips come from the book Handbook of Thermal Plasma, published by Springer. Fast macroscopic motion can produce a chemically frozen condition, where electron density remains higher than temperature alone would predict. Thermal plasma generation can be organized into two core concepts that cover most engineering sources. One concept is the electric arc, where an electric current, DC or AC, passes through a gas between two electrodes. The other concept is electrodeless plasma generation, where energy is coupled into the plasma by capacitive coupling or inductive coupling. These two concepts provide a practical backbone for understanding thermal plasma sources and their constraints. Arc operation is introduced first, because an arc is not possible until the gas becomes electrically conducting. A thermal arc requires the gas between electrodes to become electrically conducting before a stable current path can exist. At room temperature, the gas is a strong insulator, so charge carriers must be created to trigger electrical breakdown. After breakdown, a conducting channel forms, and the current through the ionized gas produces gaseous discharges that can develop into an arc. Most industrial arcs use DC because it sustains a steady discharge without repeated reignition. Low-frequency AC below 100 Hz can still behave arc-like, because each half cycle repeats breakdown and the electrodes exchange roles as current reverses. At higher frequency, ionization does not fully disperse each half cycle. Periodic breakdown becomes unnecessary, and the voltage current characteristic becomes nearly ohmic. Electrical discharges are the focus here, while laser, particle beam, shock wave, and furnace-heated plasmas belong to different generation categories. Figure 20 clarifies where voltage is consumed along an arc by showing steep potential drops near the cathode and anode and a smaller gradient through the arc column. This supports a useful decomposition into the cathode region, the anode region, and the arc column, where the arc column is the main plasma region approaching local thermodynamic equilibrium at high intensity. High-intensity arcs are characterized here by current greater than 50 A and pressure greater than 10 kilopascals, about 0.1 atm. In this regime, the arc can drive strong macroscopic flow, and changes in the current carrying cross-section can act like a pumping mechanism. For current above 100 A with axial current density variation, flow velocities on the order of 100 meters per second are plausible. The cathode jet phenomenon, also called the Mecher effect, is an example of how momentum and heat can be injected into the column. Arc temperature and charge particle density vary strongly with arc parameters and geometry, so device design must treat them as coupled outcomes rather than fixed values. Arc columns are commonly classified by the stabilization mechanism that maintains a stable arc position, because stabilization directly determines device architecture. Stability does not require a stationary arc, since controlled rotation or guided motion along rails can still count as stabilized operation. A free-burning arc has no external stabilization mechanism, yet can still self-stabilize through induced gas flow. Ultra-high current arcs up to 100 Ka are also treated as arcs, and even pulsed discharges can qualify when duration is on the order of 10 milliseconds. In arc furnaces, such discharges can show turbulent plasma volumes, vapor jets, and multiple mobile electrode spots, so no single stabilization mechanism dominates. Figure 21 illustrates induced flow resulting from arc constriction, including constriction produced by a water-cooled diaphragm. This figure highlights how magnetic self-interaction can drive pumping and contribute to stabilization in specific configurations. Figure 22 summarizes common arc configurations used in plasma-generating devices by separating blown arc operation from transferred arc operation. In a blown arc configuration, often called a plasma torch, both cathode and anode are internal, and plasma-forming gas flow stabilizes the arc while maintaining continuous motion of the arc route on electrode surfaces. In a transferred arc configuration, one electrode is in the torch and the other is external, such as a workpiece in plasma welding and cutting or a molten metal bath in metallurgical applications, and polarity can be reversed. Figure 23 shows an AR/H2 transferred arc between a hot cathode and a molten copper anode with arc length 100 mm and arc current 750 A. Figure 24 shows a transferred arc between two plasma torches over a molten metal bath, where one torch acts as cathode and the other acts as anode, and the current closes through the bath. Together, these figures make the power coupling pathway explicit, whether the target is a high-velocity jet or conductive bath. Inductively coupled discharge is a reference electrodeless plasma source where energy transfer occurs by electromagnetic coupling rather than electrodes. Figure 25 shows the core mechanism. A high-frequency current in an induction coil produces an alternating magnetic field that induces an annular electric field inside a coaxial confinement tube. The induced electric field drives an induced current in the plasma, and ohmic heating sustains the discharge without electrode contact. Figure 25 also includes an example of a 12 kilowatt inductively coupled argon discharge in an open-ended air-cooled quartz tube. Figure 26 provides radial profiles of induced electric field E in volt per centimeter, induced electric current density J in ampere per square centimeter, and electrical conductivity sigma in mho/cm at the middle of the induction coil for frequency 2.6 MHz and nominal power 25 kilowatt. Local power deposition follows the product of current density and electric field, so an off-axis maximum appears in the annular region associated with skin depth delta. Equation 14 defines skin depth delta as the electromagnetic penetration depth, and the key meaning is that penetration decreases as applied frequency and electrical conductivity increase, while magnetic permeability also matters. Figure 27 is used as a map of thermal plasma sources organized by nominal power rating in kilowatt and plasma velocity range in m/s. That mapping is useful because power level and jet velocity constrain what processing tasks are physically realistic. Plasma torches with hot cathodes are described as common sources for plasma cutting, plasma welding, and plasma spraying for protective coatings and near-net-shaped parts. The governing mechanism is resistive dissipation in a partially ionized gas, converting electrical power into a high-temperature plasma inside the torch. Stable current flow requires sufficient ionization and electrical conductivity, so gas temperature must be high enough to sustain conduction. For most plasma-forming gases at atmospheric pressure, about 8,000 K and above is a practical threshold for strong conduction. Across these sources, electrode-based arcs and electrodeless inductive coupling remain the two central generation modes for thermal plasmas in engineering practice.